and digital techniques in England, France, Germany, Netherlands, and the U.S. He was director of the Commercial Television Satellite Engineering Division of Pinzone Communications in Cleveland, Ohio. He's presently working as a consultant with Hewlett-Packard. He's developed experimental techniques and apparatus which makes the recent Fireball investigation possible. Sounds intriguing. Dr. James Corum has a BSEE from the University of Lowell, 1965, an MSEE, Ohio State, 67, and a PhD in electrical engineering from Ohio State, 1974. He's been active in academia for 18 years, serving as an associate professor in the Department of Electrical Engineering at West Virginia University, and also as a professor in the Department of Electronic Engineering Technology at the Ohio Institute of Technology. While a faculty member in West Virginia, he's received nine University Outstanding Faculty Recognition Awards, prizes, and citations. He's presently a senior research scientist with the Electromagnetics Department at Battelle in Columbus, Ohio. Dr. Corum is also a senior member of the IEEE and also holds memberships in American Geophysical Union, American Physical Society, Research Society of North America, and the Society of Motion Picture and Television Engineers. He currently holds 5 patents and has in excess of 50 technical publications. So please welcome our 2 speakers. They will co-present, and then after 45 minutes they'll take a short break and then get right back into it. So please welcome Kenneth and Dr. James Corum. May have to pass this back and forth. That's for the taping.
Okay. I'll be working over here. Let's see. You probably can only hear me if I hold this thing up, huh? All right. If at 8 o'clock in the morning my voice will wander off, and if for some reason or other I get too quiet, you can't hear me anymore, wave at me or something, and I'll try to speak up again. Let's see. Normally I try to be a little more diplomatic in our introduction and thank everybody for inviting us here, and it's nice to see so many people back again over and over again over the years. And I'll try to just cut that short and get right into some technical things. I take it that most of you are here because this morning because you wanted to hear something technical. The 2 papers that we submitted, the first one is on, I think we were able to do it without any equations. We drew lots of pictures though. And it's on, let me say, Tesla coil engineering. The second paper is on the ball lightning experiments that I'm going to say we performed, but that were completely outlined in the diary and in the various publications that Tesla had. And when you look at it in retrospect, you'll say, what a bunch of boobies we all were for not just doing what he told us to do. It's been sitting there in print for 85, 90 years or so, not just in the diary, but in Collier's magazine and other places. I mean, it wasn't that he was trying to hide something. We make the comment in the paper that was submitted that it's like Poe's story on the purloined letter. Just said it right out in the open, and that's where nobody would look. Everybody would look for something hidden or mysterious underneath it all. Also, there's some fascinating developments that have occurred fairly recently with the Soviets, and published in their open literature, and a number of books that have just come out. We'd like to tell you a little bit about that. Okay? Let's see. The first one then is on, I think the official title of the paper is something like 100 Years of Cavity Resonator Development. And cavity resonators, microwave ovens, microwave electronics as we know it today, really develops. You can trace it right on back to the work that Tesla did in the early 1890s. It's amazing that I taught microwave engineering, both undergraduate and graduate courses for a good many years. Go through all the boundary value problems and all the solutions for cavity resonators and waveguides and all that. But what's amazing is that, hey, in all that, you never tell the story of where those equations came from and who those people were. And the remarkable thing is let me say, the fingerprints of Tesla's work right on through up to the development of distributed circuits and cavity resonators and microwave ovens and particle accelerators that we have today. Okay? Now, let's see. Doesn't make any sense to talk about all this without somehow or other showing some of these pictures. Now, let's see, that's kind of low. Yeah. Somebody want to catch the lights there? At least the ones here in the front. Okay. Can we get the one that's right over the middle there? Yeah, okay. This is, of course, a famous picture, and you've all seen it, what have you. But there's something thrilling about this site, and it certainly is a shrine for electrical engineering, electrical science. You know, physical things come and go, they pass away, but ideas and concepts that are real, all right? A lot of people have wrong ideas, but I mean, people that are on the right path have ideas, and those things are eternal. They don't change. And Tesla made comments about that several times. And we should mention a little bit about some of the people that were here. Of course, Fritz Lowenstein, that was Tesla's technician here, was the first vice president of the IRE when it was first formed. And Lowenstein was also the inventor of the Class A amplifier, which is something they normally don't tell you junior level when you're learning your transistor circuits. Or back when I was an undergraduate, that was a mixture of transistor and vacuum tube circuits. They never told us that it was Lowenstein who got the original patents working for John Hayes Hammond at Gloucester, at the Hammond Labs. He was also the inventor of the shaped capacitor, you know, so that you could tune and get something that would be, say, linear in frequency. Tesla, by the way, I don't know why it's not commonly advertised, but in 1891, Alexander Graham Bell was president of the American Institute of Electrical Engineers, and during that year, Tesla was elected as vice president of the AIEE and served a 2-year term along with A.E. Kennelly, who's famous with Heaviside as the discoverer of the Kennelly Heaviside layer. As I say, Tesla was vice president of what's now the IEEE for 2 years. And a lot of people in the IEEE and the history committees don't seem to realize that amazing thing, that they forget the past, even though they're supposed to be authorities on it. Picture, of course, a lot of these were taken by moonlight by Dixon Alley, who's the photographer that... Now, a lot of you have come to this symposium, and I think it was in the 84 symposium where somebody did a marvelous piece of work and located the original site. It's at the corner of Foote and Kiowa Streets. And all of you should make a trek over there and stand on this site and look and see the mountains in the distance. And if you take the diary, you can look in the other direction, see the printer's home and so forth. But also in the background, you can see where there was a lake. And if you've got a rental car or a map of Colorado Springs, you can see Prospect Lake, which shows up in some of these pictures in the background. You can see where there's ice on the lake. Well, where did RF start? Some of you will recognize some of these from previous years, but that's okay. I have to start at the beginning and come forward to the circuitry that we'll be dealing with. RLC circuits, the second order, yeah, we want the one at the top. Start with Lord Kelvin. He's the first guy to introduce the discharge of a Leyden jar into an inductor. It's a lump circuit. Dies as e to the minus alpha t. It's a viscous damping for mechanical engineers. Actually, I think I've got a little quote on there from, or a comment to John Stone. Stone points out that the analysis by Lord Kelvin was not accurate for spark discharged capacitors. And this is where every sophomore in electrical engineer starts. You do the underdamped and overdamped, critically damped case. But I mention that because when Hertz was doing his experiments, what he did was he took the capacitor plates and just opened them out and used the inductance of the structure and used a, can we focus on just a little bit? Used an induction coil here. And this marvelous book that was put out by the history committee for MTT, the Microwave Theory and Techniques group of the IEEE a couple of years ago, where someone went back and really did quite an analysis of this. It's kind of like a photographic review. Anyway, typically had around 15 kV at low frequencies, let me say 1 kilohertz buzzer here, that would charge up the capacitor plates and reach a point where we'd get an arc here and discharge. Of course, when it does, we've got an RF short circuit. This would, the charge on the structure would discharge, oscillate back and forth, and ring down. And it radiated, of course, at a frequency that's proportional to the characteristic length of the structure. The problem here is this, and this is the reason why I repeat this. How much power could you radiate with a structure like this? You know, Tesla went to Bonn and talked to Hertz, I think it was in 1892, about this. How much power can you radiate? Well, the amount of energy that you can store up on that capacitor is a half CV squared, and C is typically picofarads. Or if you had a really big tower, maybe, you know, 1,000 picofarads or something. And a half CV squared is the amount of energy you've got, and the number of times per second you do that, dW dt is the amount of power that you can produce. And for Hertz's experiments, the average power radiated works out to be around 25 to 35 milliwatts. And it's right there in that reference. It's also in Electric Waves on page 40. People will quote and say that, well, Hertz was using about 16 kilowatts, and it turns out that that's the peak power that he had at 50 megahertz. But that's not the average power that's radiated. From an engineering point of view, that the 30 milliwatts isn't too exciting. Tesla found a way to improve this, and overnight, the amount of power radiated jumps by 5 orders of magnitude. Imagine if somebody could come along with a transmitter today and do that right now. I don't know what IMAX top transmitting tubes run, but let me be generous and say 10 megawatts or so. Seems like they have a megawatt tetroders. But suppose somebody could just go 5 orders of magnitude from that, and all of a sudden we're talking about average powers now, not peak powers, that would be up on the range of terawatts or so. All right, that would be a significant, but Tesla did that, a 5 order of magnitude jump. We've also shown this one before, but it does also set the scene. It's a critical piece of history. Early on, people were using induction coils, and a lot of people try to build Tesla coils very similar to this. And this is what Tesla had in 1891 or so in his publications. And engineers call this coupled coil transformer, and depending upon the coupling, E2 equals NE1, where N is the turns ratio, and people try to build Tesla coils that way. And we'll show you where even some of the big boys tried to build Tesla coils that way, and it's about the craziest thing you could do because they don't operate that way. And all you get for your troubles is losses. All right? We'll show you where Bright and Tove and Hafstad built one that way. And it's no wonder they went to Van de Graaff machines, because what they had was nonsense. It's probably one of the poorest design machines that you or I could ever see. All right? It's documented very well, so we can see the mistakes that they made. But Tesla's marvelous discovery was to move the energy storage device from the antenna side, use a couple coils, and move the energy storage device over onto the primary side. And that's got to be one of the major advances in the development of civilization. All right? A very simple idea. I shouldn't say it's simple. It's deceptively simple. It looks real simple. When you do some of the analysis, you find it's a little more complicated. It's no wonder Tesla didn't try to attempt a lot of the mathematical analysis. A lot of the mathematical analysis wasn't available, in fact, until the late 40s and early 50s. He also discovered the importance of spark, the duration of the spark control. Many people build machines, giant machines, and they get little sparks. You know, and the whole problem is they're not controlling this spark duration. And if you examine the sequence of patents that Tesla has in the 1890s, he stops and spends several years developing rotary brakes for the purpose of spark control. Let's see. This is an important improvement, also very important to Tesla. This version down here is the version that most people see today when they talk about Tesla coils or Tesla coil circuits that they're going to build. Normally it's turned around, but this is from a drawing that Tesla had in a report that he gave in 1898. What's going on here, of course, and you've heard this several times already in the past few meetings, is that we've got low frequency power mains here that will basically, at low frequencies, say at 60 hertz, this primary has, you know, it's only a few microhenries, so it has 0 reactance, and basically what happens is we just charge these capacitor plates up until we reach the breakdown of this gap. That's really a simplified way to describe it, but when this breaks down, we have a plasma conducting across here. It's like somebody closed a switch, and this is then an oscillator, right? Just like we had with Lord Kelvin's stuff. And when it oscillates, if this is a tuned circuit, we'll get magnetic coupling between the two, and there's an exchange of energy oscillating back and forth between the two, and energy will go over into the secondary. Things will happen, and you'll build up to a fairly high voltage on the secondary. All right? We'll have a whole lot more to say about that as the hour goes by. This version is shown in the diary. It's of interest for several reasons. First, Tesla takes this resonator and puts it over here a little bit further. And this part here is a lumped circuit, sinusoidal, it's a damp sinusoidal, master oscillator. All right? This is not a Tesla coil per se. The voltage rise here is not by standing waves. It's a lump circuit, obeys lump circuit analysis. You can verify that in the lab yourself. And today we could take all that and remove it and bring in a 250 kilowatt Continental AM power transmitter, you know, and plug it into this thing and get the same results that Tesla got. Okay. All right, that's all I want to say about that. It's taken longer than I wanted to set the stage. I guess I do have one more little thing, and this is from I think this appeared in both our books on the vacuum tube Tesla coils, and also the one on the computer program we wrote. Let me mention something about that. We wrote that program several years ago. I think it was in '85 when the traveling wave aspect of Tesla coils occurred to us. By the way, it had occurred to others before that we didn't know about, but you have to struggle and find these things out yourself. I think it was in the '86 symposium we came all excited and told everybody about it, you know. And I think maybe there were one or two people who understood what we were talking about. And so we said, all right, well, look, what we need to do is take all that mathematics and all the Smith charts and all that stuff, and you know, a grad student in electrical engineering would understand what we're doing, but let's see if we can't put it in the hands of, you know, people that are trying to do this thing because they want to build a Tesla coil, not because they want to understand all the engineering. And so we wrote those computer programs, the TC Tutor stuff, and tried to provide as all the documentation, all the equations, so you can check everything that we've done, see where we've made assumptions, and go through and get those results. And that was the purpose of that proposal. Proposal, yeah, you know what business I work in. 8 o'clock in the morning is too early to think clearly. Let's see, Lord Kelvin, again, this is sort of the history of cavity resonators. There's a cavity resonator down here, it doesn't show, but this is how they developed historically. And I've been wanting to write a paper on this because I've got all the references, and I can show you places where people like Sloan quote from Tesla. It moved on me. Sloan quotes on Tesla, and Hansen quotes from Sloan, and you can. There is a documentable pathway from the microwave technology we've got today right on back to Tesla's work. Let's see. The last one on the previous one was this double tune circuit. Oh, I didn't tell you why Tesla was using this. And by the way, this isn't really drawn correctly. I mean, this is counterset, but that's okay. But we've got one circuit that oscillates and rings down, while the other one's charging up, and then this one oscillates and rings down while this one's charging up. And we could have used more. We don't have to stop with two. And in fact, Marconi went to more. I think he patented a version in the 1907 or where he had, I think, 7 of these guys to try to get two things, a sinusoidal wave, and the second thing is more power. You say, well, it's kind of a primitive idea. No, it's not so primitive. If you look at some of the recent IEEE transactions on nuclear science, you see that virtually the same technique is being used by people at Los Alamos and in a number of other places. Okay. Now, this is what's kind of fascinating. Again, this is a resonator, and David Sloan picked this up, put the resonator in a box, okay, and developed what is commonly called today the helical resonator in a can. Hansen expanded on this. Sloan's work was done at around 40 meters, around the 7 megahertz, 40 meter ham band. And Hansen pulled this out straight, still got the resonator in the box. This is still electrically a quarter wavelength long. We still get voltage rise by standing waves. And then Hansen kept shortening as he's going up in the microwave region, he kept shortening this, and all of a sudden he ended up with an empty box with a little link couple on the side, coupling the magnetic field. But the resonator still works basically the same way. It's still a distributed circuit. The voltage rise inside there is the same. This is, in fact, a Tesla coil. Right? The physics that describes this is exactly the same physics that describes this guy. All right? We do it with the same Maxwell's equations. We have the same kind of modal analysis. The field structure is a little bit different, but the physics, the physical principles are exactly the same. There's one more I like to talk about down here, and that's when we do the whole Earth ionosphere cavity that was postulated by W.O. Schumann in 1954. And that's probably the grandest cavity resonator that I can think of that we can get our hands on. I did read in the about 20 or 30 years after Schumann's work, somebody postulated a cosmological model in which the whole universe was a cavity resonator. And it was a very fascinating theory. It was even written up in the New York Times Sunday magazine. So. All right. Now, that's a little bit of history. Let's get down to something useful here. Okay, I'm going to hold this a minute. Let me take this off. Okay. This is a standard Tesla coil. You've all seen these. You couldn't have walked in the door if you haven't seen something like this. And let me mention the following, what's going to happen here before we go into the actual drawings that describe the currents and so forth. Again, we're going to charge up this primary. There's only a few turns, and it's 60 hertz. It's low reactance, so that low impedance, so that the whole voltage will basically, a very small voltage drop here, the whole 60 hertz will appear here, and we'll get a conducting short here at RF, and we've got an oscillator that will drive this guy over here. Now, that circuit on the right cannot be treated in this version by lump circuit analysis during the whole operation of this structure. During the period of time in which this oscillator this one is discharging, the magnetic field from the primary bathes the whole secondary. And the whole secondary is just being bathed in the magnetic field of the primary, and energy oscillates back and forth between the two. There's a marvelous little homework problem in the back of Raymond Wenery, a traditional book going back to the 40s that we used to use for one of the undergraduate microwaves courses, and it tells you that helices behave two different ways. If they're bathed in an external field, the disturbance that you'll get at the terminals of the helix obeys one set of equations, and yet if you drive it another way, you get a slow wave effect, and the velocity of propagation along the structure is a whole lot different from the previous way. Now, what's going to happen is this. We'll end up with a lot of energy over here, bathing this resonator, and then the spark will break. Now, when it breaks, the impedance in the primary is very, very high. And so that energy can't come back to the primary. But it's distributed over the whole structure. And over a period of time, which we call the coherence time for the resonator, it's different from the fill time for a cavity resonator. That corresponds to a sinusoidally driven resonator. But over a period of time called the coherence time, it's very simple, similar to optical coherence, and it has to do with a fundamental reciprocity relation in Fourier analysis. During that period of time, standing waves will build up to a peak, and then the whole thing will ring down. And you can actually see this if you've got an oscilloscope, and we'll show you some of the waveforms here in a little while. Now, it's that building up to a peak time that's important. And by the way, it's during that latter period of time that this coil behaves exactly the same way as an extra coil. And this is an extra coil during that period of time. It's a secondary during the period of time when we've got the two mutually bathed. All right. Since that thing is a resonator, the voltage distribution builds up on any resonator. You've all seen resonators in the bathtub. You can sit there and splash water back and forth and build up and they call them Vmaxes and Vmins in there and get standing waves. When you first start splashing, you'll get traveling waves, and as the waves travel back and forth, they'll begin to interfere, and just like in optics, cause a diffraction pattern, and the interference pattern builds up to Vmaxes and Vmins, and the position of the nodes will stay in the same places, and the voltages will slosh up and down. The Vmins are where the RMS value is the minimum, and the Vmax is where the RMS value is the maximum, either positive or negative while it's sloshing. Yeah. Here's a curve from a recently published Russian book. I don't know if you can read Russian. The thing on the left you recognize is just a, this is the book called Industrial Accelerators by Abramian, he's now at the Institute for High Temperatures in Moscow. This thing on the left is just a standard Marx generator. By the way, Tesla patented the Marx generator in 1897. All right? The language is described. I think the Marx got his patent on it in, I believe, 1924 or so. And apparently the Germans don't read, or weren't reading American patents at that time. But this very structure is described in a 1897 patent. The language, I think there's only like 2 or 3 claims in that patent that describe this thing exactly. I'm not talking about that one today. Here's the resonator that Abramian has, and notice this is the voltage distribution. And, I don't read Russian, but I've got a number of friends that do. And the language down here basically says the thing on the right shows the voltage standing wave. Here's the resonator, a Vmin at the base, Vmax up at the top. It's a capacitively loaded transmission line. Here's the primary that goes in here, and this would go off to the capacitor and rotary breaker, or whatever other pulsing circuit we're using. And they're showing here the voltage rise waveform on the resonator. It's interesting that, by the way, this book has been translated into English. I think it's available through Hemispheric Publishing. It was translated within the last year or so. Oh, let's see. The caption on the bottom says, scheme of sources of pulsed high voltage and shape of generated voltages. And the reference is Industrial Accelerators by Y. Abramian, 1986, on page 73, if you want. You can probably find that at your standard engineering libraries. This waveform is an important one. And this is the standard lump circuit analysis that the best presentation we've ever seen on this was in, Static Electricity and Magnetism by, I can't think of his name. Smythe, yeah. Smythe has an outstanding presentation of this in the transient case, including losses. That's why I say it's outstanding. Skilling's famous book on traveling as a transient analysis does the same situation without losses. When the capacitor charges up and that break first breaks down and conducts, the primary current is what we've drawn above, and the primary current, secondary current below here. Both circuits are behaving as lumped couple circuits. And notice there's a phase shift here, and you've probably seen this kind of thing with coupled springs and pendula. There's a famous mosque in Iran. There's 2 mosques that are side by side with a walkway between the 2, and they actually behave as coupled oscillators, and their displacement of the oscillators actually behaves like this. And I guess for a good many years it was thought of as being sacred. And a bunch of civil engineers from England went down there, I think in the late 1800s, to examine what was going on, and came back completely baffled. Depending upon the coupling you have between the primary and the secondary, you have this oscillation of energy back and forth. Notice that the envelope goes to 0 at a certain time, which means that we're trapping all of the energy over here in the secondary when the secondary has maximum amplitude of current. In the low loss case, you can go through and compute what this is. In the computer program that we give you, we do the completely lossy case so you can get a very accurate calculation of this. The time between beats here is 1 over delta F. That's what the big T sub B is. If you had a spectrum analyzer, or if you know a little bit of arithmetic and compute the Fourier transform of this to get the spectrum, this is what you'd measure with a wave meter back in the old days, but what you'd see with a spectrum analyzer today, you get this double hump thing, and with a lower frequency and upper frequency that are both displaced from the resonant frequency. I've assumed that the 2 coils have the same resonant frequency when they're infinitely removed, and then we brought them together, and you get this double humped circuit. And depending upon the coupling, those humps will move together, move apart. Rated critical coupling, I guess it's just a little bit after critical coupling where they begin to diverge. Again, this is predicted on the basis of lumped coupled circuits. Okay, and this is classical analysis that you find in many places. And it describes totally what Tesla had for his Tesla coils in 1891, and fails miserably for what he had in 1898, even before he came out here. Okay. I went up at the top. We've worked a very special case. This is kind of the Optimum early Tesla coil, where we broke the primary spark at that particular instant in time, and then the secondary operates alone. All the energy is trapped over there, and it just rings down. And you can do this. You don't need Tesla coils to do this. Just like IF cans at 455 kilohertz in a regular receiver do this kind of thing. This is a transient response. And just couple tuned circuits to this. Notice it built up and then rings down over many cycles. Okay. The interesting thing here is during this build-up time, we have that double-humped spectrum. And then after it breaks, when it rings down, if you took the Fourier transform of this part, or look at it on a spectrum analyzer, you'll see a very sharp line. It's a Lorentzian profile, for those of you that are atomic physicists, for this kind of structure with the viscous damping. All right. But all that works for lumped circuits. When we were over in Belgrade the first time, we didn't know about this. It wasn't too long ago we didn't know anything about all this. Other than, you know, we'd all built circuits. I think I've been licensed as a ham radio operator since 1956. I think it was 54 when Cosson and the other fellow came out with that article on vacuum tube Tesla coils that appeared in radio, TV, whatever it was called back then. It's now radio electronics. And we built one of those and burned out some tubes and grids and stuff like that. But really didn't understand from an engineering point of view. You know, an engineer is different from a scientist. A scientist just wants to know how things work. An engineer wants to find out how they work, but he wants to squeeze that last bit of performance out. And the real mechanical engineer is the guy who goes down and spends $20,000 on a car and takes it home and pulls the engine out. You know? To me, that's an engineer, because you want something more than what he could buy. All right? Now, the first time we went over to Belgrade, Dr. Morencic pointed out to us a reference that we'd overlooked, and it was one that was in, it's listed, by the way, in the diary, and it's that paper by Fleming and Dyke. And they have a very fascinating discussion in there that describes this very phenomenon that we have here. By the way, everything I'm telling you today is in the paper. We gave it to Steve Ellswick when we came in here on the first day, so that this is all documented, and I suspect that eventually you can all get copies of it and see everything that we're saying. What? What? No? In 2 years from now, right? Okay. Look, here's what's of interest in the Fleming and Dyke paper. When they took a wave meter, right? Now, wave meter is a tuned circuit with a little indicator on it, and as you change the frequency, you can get relative amplitude of the response. So it's equivalent to what we'd use as a spectrum analyzer, except for the fact that it can't show you stuff in real time. Right? It does a long time average. They measured this solid curve, which has the 3 humps. All right? And there's an interesting discussion that goes on in there concerning the duration of the spark. And Heckley's discusses it also with Dr. Fleming. And but the upshot of their long discussion is this: that the dark curve that Fleming and Dyke measure is actually made up of these 2 separate curves. And during the period of time when the primary spark is conducting, and both circuits are interplaying, and we're getting that for those of you that are ham radio operators, you recognize that the spectrum that we had down below there, and that was a double sideband signal. All right, the Fourier transform of that oscillating exchange signal is a double sideband signal. During that period of time, when the primary spark is conducting and the entire resonator is being bathed, the structure is behaving as a double sideband oscillator. We've got the 2 humps at 2 separate frequencies. And then when the primary spark breaks, all the energy is trapped in the secondary, and the secondary rings down as a resonator. All we get is this middle curve, and that's all there is. All right. And by the way, this middle curve is characteristic of the bandwidth of that curve is characteristic of the losses that are in that distributed resonator. In a lump circuit, we'd say it's proportional to the Q of the resonator. Q has a little bit different meaning when we talk about distributed resonators and cavity resonators. It's not just omega L over R, it's something a little bit different, but for lump circuits, it reduces to that. width of that curve is proportional to the losses, and if I make the losses go down, I'll get the same energy. The width will get very thin, and the peak will get very high, and that's what Tesla was doing. Right in the diary, you can go through, do the calculations where he's running this stuff, and I got to talk faster, Kenny's saying. Okay. Now, here's something that is very exciting, all right, that Fleming and Dyke missed. I'm showing VC2 here, all right. That's the voltage on the top of the ball or the toroid or whatever you have. We've got two separate instances of time. Up until at this particular instant in time, the primary spark is conducting, and we've got the interplay of currents back and forth between the primary and secondary. And right at this instant in time is when the primary spark breaks. All right. Now, when that occurs, if you've done it right, all the energy is trapped in the resonator. All right. And with that Tesla coil, we're now going to make the transition from lump circuits to distributed circuits. And with all that energy trapped over there, and it's distributed almost uniformly over the whole coil. I should mention, for those of you that are EEs, the best analysis of coupled transmission lines was given by R.W.P. King. It's the same King that did the thin linear antenna up at Harvard, and whose grad students are now doing the electromagnetic missiles and all that stuff. But King has an outstanding treatment of that in the late 40s in the Proceedings of the IRE. There's 3 papers in there where he discusses that distributed resonance. But when that energy is trapped over there, what happens is you go through a period of time where that energy starts to build up standing waves. Now, while it's building up, it's also being dissipated. And so you reach a point in time where the standing waves have reached up to a maximum, and then all of a sudden, or I don't want to say all of a sudden, and then from then on, the dissipative processes in the resonator take over, and it dies down. Again, the primary spark is broken here, and there's this really dramatic rise in the envelope of the voltage in the resonator. It's during this period of time, from here out to here, when the voltage is building up to a maximum. Now, there's an assumption built into all this, and that is that there's no discharges taking place. We're looking at right at a linear system here. When discharges occur, there's another way we can handle that. And all I'm doing is making sure that the ball on the top is big enough to be able to handle the potentials that we're going to hit when we get up here at that particular point. So the standing wave builds up during this period of time, and then the whole resonator decays exponentially after this. Now, here's what's fascinating. Back here again, we've got the double-humped couple lump circuits with a double-humped spectra. At this point in time, we've got the single, let me call it monochromatic spectra, although it's got a certain finite bandwidth. It's a bandpass signal, right? This little portion was what Fleming and Dyke missed. And as I say, you can see it with an oscilloscope. Now, we wrote an appendix that we prepared for the TC tutor. It's not in the version here that's for sale. We're still typesetting it, but in it we go through and derive all the equations on the spectral coherence of cavity resonators, and helical resonators included, and derive the analysis for this portion of it. Those of you that have backgrounds in optics will recognize it immediately. Okay, the analysis is very similar to what you do with an amplitude splitting Michelson interferometer when you can measure the self-coherence of a radiation field. Now, we thought, well, that's marvelous theory. Theory's great, you know. And Kenny and I have this situation where we've had all kinds of theories and then gone in the lab, and it was, you know, had nothing to do with what the theory, what we thought we had nothing to do with what was measured in the lab. Now, it wasn't because the mathematics was wrong, because that's what's puzzling. You can do perfect mathematics and still have nothing to do with reality. It's the assumptions that go into the model that's built in your mathematics that make all the difference. Okay. Now, let's see. Here's what we actually measured when we went in the lab to see if this was so. Kenny's going to talk about this a little bit, but let me mention this. There's something important occurring here. This is the point in time where the switch, the primary break, is going to occur. We're doing this with a Ford buzzer. Kenny's going to tell you about how that's done. With the big coils, we run, with a typical rotary brake, 800 brakes per second. The spark duration in the primary will be around 100 milliseconds or so, 100 microseconds. You'd like to get it a whole lot shorter than that. And in the literature that we published, we show where the optimum for Tesla's machine was around 10.4 microseconds. And of course, there's no way you could get a breakdown there, but a break at those speeds, I don't mean breakdown, you'd get a tremendous breakdown there. But this scale on the left is in volts. We just brought everything down low in voltages and just are shock exciting this guy. And this is actually, it's kind of rough to see here, but it's actually the interplay between the primary and the secondary until you reach this point. Now at this point the voltages began to rise so fast we couldn't, we had to change scales. Otherwise we couldn't show it. By the way, the first 150 microseconds aren't shown. They go back to here, and that's where the interplay between the primary and the secondary is occurring, and this is the point where the break occurs. At this point, change the scale on the left by a factor of 10. All right? So this point, instead of being 100 volts, is 1,000 volts. All right? So 1,000 volts, we're up on the roof someplace here. And it doesn't really build up like a step function here. Actually, this is real data, so that you can see that we've got some above and some below, and it's a little wobbly in here, but you can see the general trend of this. Kenny, you want to tell a little more about this since you took the data here? Oh, yeah.
Okay, I just want to interject a couple of footnotes for you guys that like blisters. Let's talk about the real world for a moment. This data here was taken painstakingly over a period of about a month, okay, working 16 hours a day just to get this graph. Now what we did to set up the experiment to get this data and take the experiment over and over and over and over again until we could tend to see a trend and coordinate things so we could predict what was going to happen. What we did is we had a very large coil similar to the one that Bill Wysock has out here on display, and that thing would generate 20, 30-foot lightning bolts easily that when we had it in full power, full operation. But what we couldn't do is we couldn't plug an oscilloscope on that huge lightning bolt. You just couldn't do it. The electric fields were so high that the oscilloscope would go nuts even quarter mile away. You'd get spikes all over the place. You couldn't measure it. So we did take I had a 1924 Model T Ford that I owned. I just recently sold it. We pulled one of the buzzers out of it, one of the spark coils, and we connected it up to the primary and used the buzzer as the gap and so forth. And what we began to see was, sure enough, using a real nice Phillips oscilloscope where you can expand the waveform and reduce it down and look at narrow segments and trigger on different parts of the waveform, we began to see this. The interplay while the spark was conducting, we could trigger at any point, when the spark first ignited to the point anywhere in between to where the spark just went out. We could look at that. And as we began to zoom in, we could see the phenomenon that everybody saw with lumped coupled circuits quite easily. You'd get the beats and everything would go along. But what we saw was all of a sudden, right here on the secondary side, this rise. And we said, wait a minute, what is that? Where's that coming from? And we began to look closer and closer at it, and it didn't make much sense. We were saying, well, maybe the oscilloscope's going nuts, even running just a couple of kV off the top of this big coil that we had. So we began to do the experiments over and over and over again, and this graph is what resulted. For you Macintosh lovers, this was drawn on a Macintosh, so we used one of their graph programs. But this time where it's rising up was very interesting to us. We started looking at other coils that we had. We had small coils, tabletop coils, we had big coils, we had coils that ranged all the way up to 100 megahertz or so. And we began to look at this time, and they were different on every coil. We said, what's going on? What is that? What's taking place on the secondary in here as it builds up right after the spark extinguishes? And we found that we could modify that time in there by essentially changing the Q of the coil. Okay, if we had a very low Q, we would see that time change. If we had a very high Q, we'd see it switch the other way. And what we did is, as we began to play around with that, we began to see certain phenomena take place, and that leads into the ball lightning stuff or the fireball stuff. We got to be careful because we don't want to call it ball lightning just yet. It's got characteristics of natural ball lightning, okay? What we want to do is call it what Tesla did, fireballs. And this duration in here, this time, this buildup, had a lot to do with the formation of the fireballs, which we'll see later on. And then it would continue to ring down. At this point, I'll turn it back over to Jim.
I'm going to jump ahead here and skip the because I do want to get to the Livingston chart. For those of you that this is from Born and Wolf, and it has to do with the interference of partially coherent waves. And what I want to mention is if I've got fully coherent waves, so you guys that are operators, monochromatic, completely coherent, I can get pretty good interference patterns. If it's only partially coherent, if it's completely incoherent, even though it's monochromatic, I'll get no interference. All right. The same thing occurs on during that build-up time on a Tesla coil, and we discussed that in other things, other places. Here's a famous Tesla coil that was built in Germany by Werner Heise back in 1964. My German is nicht sehr gut, but Verlauf, I think probably means presentation or something, I don't know, of spanning the voltage against the earth. So he's plotting the voltage to ground for his Tesla coil. He has marvelous pictures of this thing. I don't have time to along the secondary coil of a Tesla transformer for the case where the secondary is a quarter wavelength long, where L is the length of the wire of the secondary coil. And it turns out he's got the right idea, but it's not. What you want is a quarter wavelength from here to here, which is pretty close to what you have along the wire, simply because the velocity factor for along the wire isn't too far different from what you get if you actually calculate it rigorously and formally. I include this one because it was published in ETZ back in 1964, but you can see he has the very standing wave that we're talking about here. Okay, so, and there's some pictures of his coil in action, and it looks a little like Bill Wysock's coils. Okay. I skip all this stuff. This is worth taking a look at real quick. Again, simply because this is the helical resonator against ground. All right, has a certain velocity factor. Sloan put it in the can. We can operate it openly against ground like you would. Those of you that are ham radio operators know how a quarter wave tower works. You know, if you could measure the current distribution on your tower, you see the current goes to zero at the top unless you have top loading. And then you have a maximum current down at the bottom. You can actually measure the current and there'll be a maximum. And the V does the opposite because the tower behaves as a resonator, behaves as a lossy resonator, and the loss is a radiation resistance, hopefully nothing more, maybe some ground resistance as well. But the same thing is occurring here. And this is sort of a base-loaded vertical tower. And then you can make it shorter by capacitively loading the thing on the top and all that. And the analysis of this is very well treated in other places. Do I need to show that circuit? We're going to run out of time here. We go through in several places and show you how you can treat this on Smith charts. I don't want to stop and talk about that. Let me talk about some coils that people have built. This one, Mysovsky in the Soviet Union. This is a marvelous paper that was published in 1976, I believe, by Grenberg in Soviet Physics Uzbeki. And those of you that can read Russian, Kenny and I have an article on ball lightning that was published in the April issue in Russian in Soviet Physics Uzbeki. Last summer, I had a gallbladder attack and was flat on my back for a while. Kenny had a broken back. And while we were in this tortured condition, one of my colleagues at work sent me this note that there was a conference on ball lightning to be held in Moscow at the Institute for Advanced Studies, and we had this request, would we be interested in submitting a paper. So my wife put me in the car and basically hauled me in the horizontal position up to Windsor, Ohio. And Kenny, his wife was wheeling him around in the yard in a wheelbarrow. And so the two of us got together on the living room rug, flat on our backs, and put together this paper that we sent off to the Soviet Union. And I should mention this, that what's of interest to the Soviets is that they have a remarkable theory based on fractals. All right? This guy, B.M. Smirnov, who has got to have been divinely inspired to have written some of the things that he's done. I mean, he's a very very qualified person technically, but had a tremendous amount of insight and saw how you could use Mandelbrot's fractal theory to describe some of the things that are going on with ball lightning. We'll talk about that next hour. But Grenberg, this guy Mazovsky back in the 20s was interested in building relativistic electron beam accelerators. Now this is 10 years before Ernest Lawrence and so forth over here. And really what we've got here, here's the primary going around this guy. He's got it encased in a can that's grounded. Here's the secondary resonator in there. And he's got it in a vacuum and so forth. But this was first presented as a paper, I think, at Petrograd in 1922. And you recognize that, again, he's where Tesla was in 1896. That's a very famous Tesla coil in the Soviet Union. Here's one that is in Livingston and Blewett's book. And this was the one built by David Sloan. I'm not sure if he's still alive. I came across somebody while I was at Los Alamos at an ultra-wideband radar symposium back in March who worked with David Sloan for a number of years. These are real people. Sloan built a 7 megahertz oscillator up there. And where did I put that little antenna? There it is. It gave me at the APS symposium. This is a primary. We've got a monochromatic signal generator here, so I could take that away and put any oscillator I want here. It's he's running Class C. I forget how much power he was running. Let me think. Oh, the number. This is reported in that 1935 article by Sloan in Physical Review. But again, this is the extra coil standing there as a resonator, and he built it up to about 800 kV or so. His purpose was for making X-rays. In the book we mentioned, in the paper that goes with this, we mentioned that Sloan's advisor's mother was very sick and had cancer, and so Sloan built this thing to make X-rays and used it on his advisor's mother. Boy, that would have been a marvelous thing to do. I'd have loved to use it on my advisor occasionally. And she was the first one to be successfully treated with X-rays for stopping cancerous growth. His advisor, by the way, was the Nobel laureate Ernest Lawrence. Okay, E.O. Lawrence. This is of interest because this is a famous Tesla coil. It's the one that was built by Hafstad and Tove and those guys in the late 1920s. They used 7,000 turns of number 40 copper wire, which has, if you get TCBA news, which if you have any interest in Tesla coils, you must get a hold of Harry Goldman and buy every one that he's ever published all the way back, because those are certainly collector's items. Somebody sent in something that was very similar to this. The guy, I think, had built like a 10-foot coil and wound it with number 40 gauge copper wire and had 10 million turns on there, and was wondering why it didn't work. And I think Harry's comment with tongue-in-cheek was something to the effect that, I've never been stumped before, but you totally baffled me on this one. What's happening here again is that for the frequency these guys were at, and I forget which it is because it's mentioned in the Physical Review article. It's the lead-off article, I think, in 1930. This is going to be a half-wave dipole instead of a quarter wave. So these guys are running it not as a vertical monopole, but as a half-wave dipole up in the air. All right. End loaded, capacitively loaded. You can go through and run this thing on, take the numbers right out of Physical Review and put them in TC Tutor and run through and calculate the operation of this thing. What you find is that the losses are horrendous because of the... I mean, what you want to do is you want to build that as low loss resonator as possible. By the way, this is his primary that he's got around here. Centrifuge. This is just a link couple. Ham radio operators do the same thing quite often. You put a loading coil in the middle of an antenna and link couple it instead of, if you don't have 50 ohm coax, you can use an open wire line or something. But they then took it and they put it in an oil bath to raise the voltage on the thing. By the way, the capacitor bank in this article is a photograph of it. They built this out of glass windows and tin foil or whatever, the same way a lot of you guys probably have done things in the past. The photograph is identical to a photograph that was published in, what's it? It's something like wireless electricity for boys and girls or something like that. It's published in 1916. They replicated the same capacitor. I mean, to the very joints. They must have handed it to somebody and said, build one of these things. Again, this has got to be one of the poorest designs that we have ever seen for Tesla coils. And you'll say, well, what would you do if it made it better? Got rid of that 40 gauge copper wire and made it half-inch diameter copper tubing or something. I mean, you want to keep the losses down. use Litz wire. Litz wire, again, was invented by Tesla. So I think there was a question on that yesterday. And the Germans picked up on it. That'll keep your RF losses low as long as your frequency's below 500 kilohertz or so. Above that, Litz wire doesn't work so much. A very poor design. These guys, by the way, wrote the article that eventually they said, well, we just couldn't use Tesla coils. And they went to Van de Graaff generators. And it's no wonder they went to Van de Graaff generators. I mean, they had built this thing so poorly, they needed, several megavolts to do some of the experiments that they were doing. And like I say, it's no wonder they went to Van de Graaff machines. They couldn't build one of these things. Now, we shouldn't be too hard on them because Chadwick, the guy that, I'm going to stop in just a minute, the guy that discovered the neutrons, made the comment that he tried to build a Tesla coil when he was for an accelerator in the early 1930s while he was working, I think, with Rutherford. I may have him mixed up with somebody else. He said, I just didn't have the training and I wasn't capable of doing such things. He recognized that there was something going on that he didn't understand, and he just set that all aside and went another way to do it. What's the connection between all this and fireballs? This is another form of a Tesla coil. This is a helical resonator in the can. This is one Kenny built. I forget what frequency it was working at. Is this 2 megahertz, Kenny? Yeah, 2 megahertz. And the Q here is about 450. This guy was 3 feet in diameter and stood about so high, a big barrel, And we began to notice strange discharges from this thing. And it was right at the time when we came out here in 1988. And at that point in time, we were also reading this thing that it was in July, I think, of '88 that Harry Goldman had published this statement in an article called Tesla Tries to Prevent World War II. But he's describing how he made fireballs. And he says it became apparent that fireballs resulted from the interaction of two frequencies, a stray higher frequency wave imposed on the lower frequency oscillations of the main circuit. Now, what's he talking about? This condition acts as a trigger, which may cause the total energy of the powerful long wave, that's the low frequency, to be discharged in an infinitesimally small interval of time and at a proportionately tremendously, boy, don't you like his language, at a proportionately tremendously great rate of energy movement, which cannot confine itself to the metal circuit and is released into the surrounding space with inconceivable violence. Now, this last phrase here, released into space with inconceivable violence, is very important with some work that it's very analogous to some work that Forrest and Witten were doing on fractals in the early 80s, and I'll tell you about that in the next hour. And then he goes on and he says, well, it's only a step from learning how a high frequency current can explosively discharge a low frequency current to using the principle to design a system which these explosions can be produced by intent. And Kenny and Leland Anderson and I and Danny Edwards were walking around Prospect Lake. And Leland made the comment. He says, it's amazing for all the Tesla coils that have been built that, more people haven't been seeing fireballs. He says, the way Tesla described them, they almost come off like bubbles off the machine. Why aren't we seeing them? And it was a puzzle. We just stood there. By the way, most of the stuff that is really exciting that goes on in the symposium doesn't occur here at the podium. It occurs in the parking lots and the restaurants and the parks and in the airport. It's almost a Roman orgy of explosive intellectual activity that occurs at a symposium. And there we were banging our heads on the wall. And we flew back to Cleveland, looking at the diary, reading this stuff. As you look at the pictures, it becomes obvious what's going on, where Tesla has one primary exciting several secondaries, and he could use easily one coil to discharge another. So we arranged, when we get back, we arranged the circuit in that form. Sounds real, that's an easy thing to say. I think it took Kenny about 10 days to do this. And you recognize those two coils in the center. That's a drawing very similar to what Tesla has in the diary. I forget the page number. It shows up many places, but I think early in September. Those of you that have a diary, start reading through September, and you'll see where he's actually got that same kind of circuit. The actual form of that's not what's critical, but the general circuit ideas there. By the way, we publish all the numbers that are measured to completely characterize those coils. So if you don't believe us, you can build your own and see that it's really so. Now that's the end of what I wanted to say this morning. There was a third paper that we were going to give, but Dr. Puglielli from Battelle had to be in the Caribbean this week. I understand there was a hurricane down there. He was right where the eye of the thing is, so he's probably had a good time. But he's a high-energy physicist originally from Brookhaven, and was also, I guess, in Annapolis and a few other places. And as he began to read some of Tesla's work, he said, boy, you know, he says, some other strange things are going on here with respect to the X-ray apparatus. And anyway, we were looking at this Livingston chart, fairly famous. It's a plot of accelerator beam energy versus year. And Livingston is the guy that started plotting this stuff. Starts around 1930 or so, around 100 kV. And over the years, certain things have happened. You can see way up there is where the superconducting super collider is supposed to be at. Let me call your attention to the Van de Graaff's machines, which are these electrostatic generators. They build up real fast till about the early 40s, and somehow or other, there's a great deal of improvement after those. I think this is the newest one that was just built at the tandem version that was built at Yale. Now, what struck me as I looked at this was, hey, if I plotted on here Tesla's published, the energy is measured here in electron volts, and this is actually volts for Van de Graaff. So if I did the same thing as you do for Van de Graaff, these aren't real volts, by the way, all right? This is probably about the limit of where real volts stop. These other things are kinetic equivalent volts, all right? I don't have time to talk about that. But if I plot just like we do for Van de Graaff generator, where would Tesla's published data fall on this thing? And the thing that struck me was this. Well, there you get the idea. Here's Tesla's data. Starts out early 1890s. And lo and behold, he has his own one-man Livingston chart that is the same as this, displaced 40 years over. And the point that I make, and I really get out of this, is that, hey, we should have had superconducting supercolliders 40 years ago. Another way to put it is this: where will high-energy physics be 40 years from now in the year 2030? Let's see. We found, when we were doing this, that it wasn't necessary to use 2 coils. You could do it with 1. In the paper that we sent over to the Soviet Union, we just show the same thing with only the 1, instead of using 2 resonators, one to discharge the other. When we built this, we didn't start seeing fireballs, of course, the first time. But where we were in the diary was on page 330. And there's a paragraph in there that says, where Tesla's writing and describing this stuff. He describes it in about 4 or 5 different places in there. But he says, as already noted, a streamer will show sometimes 1 or more points of great luminosity. And what we found out was that we got an arc between these 2 guys. There'd be places where there'd be a hot spot in the middle, great luminosity. That's fairly common. A lot of you guys have probably seen it also with your own machines. But what occurred to us was, he says, in this instance, here described, the streamers were very powerful, and the spots, when they appeared, were about an inch or possibly more in diameter, actual fireballs. So in one sentence, he's talking about these hot spots. In the next sentence, he's got fireballs. So we knew we were within a sentence of where he was at. One can barely note a small luminous patch on the streamers. And you'll see some of these slides we're about to show where you can see the bright patch. At least I think you can see them. On the streamer, and the impression of the central portion of the ball. All right, so he goes right from one to the other. By the way, when we were doing this experiments, it was in mid-August of 1988, just after the symposium, and by October or so, we felt like, well, hey, what else can we do with this stuff? And that's when we said, well, can we make them go through windows? People talk about them going through windows, you know. And so Kenny got a piece of glass and set it up there. And this is just to orient you, so when you see the slide, you'll see what we're talking about. And then here's the fireball that's coming in from the fireball and a discharge coming in from the left. And the arc, the discharge hits the plane of glass, and the glass was, what, about so big by so big. It was a pretty good size, something we took out of a barn up in Ohio that had been there for a good many years. And the arc comes through, and the ball's formed on the other side, and this ball goes out. And you can see it pretty clear on the video. And if you're watching it in real time, you get the appearance of the ball incident on the left and the ball exiting, emanating on the right. It looks, in real time, looks like the ball is actually passed through the glass. The explanation for this was actually, I think, anticipated by Finkelstein and the other fellow back in the late 60s, where they give an explanation for this, and also in their American Scientist article in 1970. Well, we've got a number of slides to show you, and Kenny's going to show them to you right now. Yeah. Well, let's see. While Kenny's getting set up, I'll